I'm going to talk today about big data in the cloud. First about myself, I work in Google in the Berlin office now, but I've been in Google for about 8.5 years now. And I started as a network engineer. So my background is networking infrastructure and network engineering. But for the last 3 years, I've been working on the Google Cloud Platform. And the region kind of expanded now, covering Northern, Central, and Eastern Europe. Yeah, it's my second time in Estonia, so I'm always happy to be back. Unfortunately, last time I couldn't be here. I have with me my colleague, and I don't know where he went, Jens Bussmann, also from Google. He's in sales, so he will take the contracts at the end. Yeah, and so basically I'm going to start, and I'm going to tell you first what is this Google Cloud Platform. Maybe it's not so popular. Many people know Amazon Web Services. Not everyone knows Google. But what is our idea? Why do we make our own cloud platform? Well, it's the idea that we've been working on data centers basically since Google started existing 17 years ago, and has been building out infrastructure for the own Google products, Gmail, Google Maps, etc. since this time. We've been building the network. That's what I was working on. We have a fiber network around the globe to Asia, to the US, or from the US to Europe. We own quite a lot of fiber ourselves. And we also build a network which is quite far-reaching, going to like some corners in Africa, Mombasa, in Kenya, etc. So this is one of the things we're very, very proud of. We built together with the data center infrastructure. But the other thing is the software we built. Lots of papers have been written about Google technologies in the last 10, 15 years. And some people have copied some of these things. Some of the things I will talk about a bit. That's why I don't go into this. And all of this, our data center infrastructure, our network, and our software innovations is what we're trying to bring together. And we want that not only the Google engineers can use these technologies, but also engineers from somewhere else. Everyone should be able to make use of the platform we built. And that is the idea. That is what the Google Cloud Platform is. Especially today, I'm going to talk, so this is all the products in Google Cloud Platform, starting from basic computing, etc., storage products. Today I'm going to talk about the big data products especially, and we have several big data products. There's Google BigQuery, it's an analytics engine. There's Google Dataproc, which is basically, if you know Hadoop, it's running a managed Hadoop service. There's PubSub, there's Datalab, and there's Dataflow. And basically, we want to talk about the whole cycle of when you process data, like storing it, capturing it, processing it, analyzing it. And we have different solutions for all of that. But especially today, I want to talk about Google Cloud Dataflow. I was asked, I heard it was very popular, and people want to know more about it. It's a tool for building data pipelines, making data analysis simpler, and this is what the talk is mainly about. But probably you've heard quite a lot of these big data talks, and you can't hear this word anymore. Big data, big data, big data. I don't want to hear it anymore. Please don't say it one more time. So we need to kind of think about why do we talk about big data, what it is we're thinking about. In Google, we have not used this word in the past until it came from outside. For us, it was just data. And then we realized for others it's big data when it doesn't fit on maybe one server anymore, or in the memory, or whatever. So I'm going to talk about how we process data at Google, and going to start with what kind of data there is in Google we could think of over the years, and we need to handle, and how we do this. And I mean, we can have different forms of data. We can have small amounts of data. We can have bigger amounts of data, like might not fit on one server anymore, but it's still kind of the same. It has a lot of elements in it. They are different. We can have so much that we kind of need to separate it into different chunks, let's say by day. we separate it in different files or different databases, etc. So it could be really, really big. But usually, when you're an application programmer, you don't care about it. And my example I bring later in the demo, it's a game. So, but it's kind of the same with any kind of application you write. You don't really care about where the data come from when you write the consumer app. It's not like you have amount of data and this never changes and this is the size of your database. But you have like some kind of data always coming in. So for example, in an online game, something is always happening and events are coming in from the users all over the world. And the thing, it's not only when the data is coming in, like you can see here, the data is always flowing in, but it's also when it's happening in the real life. Like there are delays. For example, a game might be offline and then only when it goes online it sends all the game details. So it can happen that obviously if there's no delay, an event which happened at 8 o'clock comes in right away after 8 o'clock. But it can also happen that it comes slightly later, or maybe the guy was on a very long plane ride, turned this data off, and the event comes only in much later. So there's kind of two times. There's the time when the thing happens, and for these three kinds, it's all 8 o'clock. And there's the second time is when the event actually comes into the system. And this is different, and this makes it a bit more difficult to process that data. And we've seen a long time ago in Google, there are several trade-offs you have to think of. Do you want complete data? Do you want to have a low latency? What is the cost for processing this? It's always a question as well. And it depends a bit always on what to do, and you can't obviously have everything. For example, when money is involved, when you want to write the bill at the end of the month, or when something happens with money, usually it's important that you have complete data. Everything else is not so important in this case when you process it. It's quite different when you say, I want to not provide you the final bill, charge your credit card, etc., but I want to give you an estimate of how the cost is. For this, yes, we still want to have somewhat complete data, but it's much more important that we give you a fast estimate, because if we only give you a day later at the end of the month, then we might as well send you the bill. So it's a little bit different. Another thing is abuse. In any game, for example, or also in our systems, we see abuse, and it's very important that you catch this one fast so you can turn it off. You don't need all the points, you just need to find enough data to make a decision. Okay, this for sure is abuse. There's always clicks at the same pixel 10,000 times a second. I don't need to wait until the month is over to say this guy is cheating in the game. And however, when we want to build the model for this, what is abuse, what might not be abuse, we might care a lot less about the latency, because we don't run this continuously, but we need to run this at a very low cost. So this needs to be something we optimize for cost. So in Google, we had lots of these different kinds of data processing stories, depending on what we do. And these were just some examples. And so over the years, we decided for different kinds of things, we need different technologies. And we wrote quite a few papers in Google in the big data space, and I'm going to talk about these three today: Mapreduce, Flume Java, and Millwheel. And they're all used in this product called Dataflow, which I will talk about as well. So Mapreduce, who here knows what Mapreduce is? Okay, about half the people. Mapreduce was used in Apache Hadoop as well as the main programming pipeline, and it was invented at Google at about, I think we published a paper in 2002, so since then we've been using it. And the idea is, if you have a lot of data, you chunk it up in different chunks which you can fit on one server. And then you distribute it across different nodes, mapping nodes. And these mapping nodes, they do something with the data. They transform it in some way, they parse it in some way. And this way it can even work on unstructured data, because it can work with any kind of data as long as it fits in one server then for the first step. And it does like these steps in parallel on different virtual nodes and different instances. So then the second step is this data comes out and obviously has different results. And then the mapper needs to decide where it goes for the second step, the reducing step. It moves the data to specific reducing nodes depending on what kind of results you get. And this is a shuffling step. And then there's usually a smaller number of reducing nodes, which then produce a result. In the next step, they already get some kind of pre-processed data, and they emit the result in the end. So this is what happens here. This is like in very few seconds what Mapreduce is. And it's a very powerful tool. I mean, Apache Hadoop, very popular, used a lot of ways. Not very easy to program, but you kind of get used to it, and you kind of get used to thinking, how can I fit one problem in this Mapreduce way and make it in two steps. So always the results fits in a single server, but in the end I have this result of this massive computation. So we started using it for absolutely like any kind of problems, organizing log files, organizing analytics over our ads, over the search index, etc. For many of our products, we used it all the time. But it was quite hard to do when you came new in, and when you never wrote in Mapreduce, and it's kind of a different way of programming. It's not how you learn programming in university, kind of, because you need to change the problem in your head. So a couple of years ago, we invented Flume Java, which is a higher level API where we have more abstract ways of processing, where you say, okay, I bring this data in and I want to do something to it in parallel, and you just say what you want to do, but not how you fit this in the Mapreduce. And the Flume Java system that optimizes the processing around to convert it in kind of this Mapreduce framework. And what you do is you build a graph of transformation. You say, first I want to do this, then I want to do this, then I want to put two inputs together and do something else on it. And do all that in parallel, please, so it doesn't take forever. And so this abstracts a lot of the problems, and it makes it much easier to write more complex algorithms. So this was very useful. To structure data and to bring data in other form, to transform data, the same way it was done with Mapreduce. And you can do that over one piece of data, you can do that over every day. If the data becomes really big, you might do this on every, basically, file where you have the data from a day. You can even say, okay, I don't actually care about the whole data set, I care only about an hour, and then you can do this again and again, and you create a result for every hour of the day, for example. So you can do kind of this time-based windows on it by just running the same thing again and again. It becomes a bit more difficult when you think about, well, how users actually work, and especially we run on the web, other people do games, and it's kind of the same for both. We don't think in these hours in our day. What people care about when they think about the web is usually sessions, like how long was this person visiting my website, even when he was visiting again later the website. So we try to sessionize the data by seeing, okay, if there's at least 10 minutes between it, we call it a new user session starts, for example. And this is a very nice way to organize the data. Google Analytics is how people want this, etc. And if you run this on the same kind of algorithms, this might work very well. Lisa, a very nice person who always comes online at 9 and then again at 3 p.m. and does the same the next day, it works again. But if you have someone like Jose who's coding the whole night, then it doesn't work, because suddenly you have these two data sets and then you have the two results, and the one session ends here at midnight and the next session here begins at midnight the next day, but it's really one session. So to find any kind of break doesn't really work when you have such an infinite data set. So we needed to think about the way to structure such data more continuously. Like if you don't have a search index, but if you have user data coming in, this doesn't always easily work with the traditional Mapreduce. So that way, this third technology comes in, which is called Millwheel. And Millwheel was created especially to create these problems when data is continuously coming in and you want to continuously process it, because you always also want to have a result right away. And it's kind of the same that we provide an abstraction graph over this data, a directional graph, which shows how the data flows through the system, and it gets transformed with simple transformation over the time. So elements can always flow through, and there comes a result out of it. However, this was done for simple transformations, element by element. So we can filter, etc., and we can maybe do simple calculations, transformations, and this is what helped us on kind of the streaming data in the first place, if you look at Millwheel. Also helped on, but sometimes you don't just want to do the simple transformation. Sometimes you also want to do like aggregations. You want to run everything in 1 hour. You want to have these windows. Sometimes you want to have sliding windows. And sometimes you don't care when the event comes in, as we talked about before, but actually you want to bring together all events that happened in a specific space. And this is especially what we look in today, where it's especially important when an event happened and not when an event was processed, or when an event came through the system. Also, not only in fixed window, but you want to sessionize this, and you want to say, when do we have how many user sessions, for example. This is another pattern we want to be able to work with. And when you look at this, you always need to think of, well, generally, if you run such a data pipeline where you run several transformations, you have an amount of time this takes the whole transformation. Sometimes it's, I don't know, some milliseconds if it's a very simple calculation. Sometimes it's a few seconds. And depending on how much data comes in, this changes over time. So if you look here when an event comes in, and when an event gets processed, this line is ideally when this would happen. If calculation took no time, if everything was transferred through the network immediately, then everything would be processed immediately. In reality, the line looks more, it changes. And this is kind of the skew between the event and the processing time. And so what we call this is, this time is a watermark. And so what is the watermark? It is the time where we expect something to come in. Like, as I said, it might change how long it takes the data to process through the pipeline. But we expect at this time that all the data is there. So for example, here we expect all the data up to this event time is here. And this is kind of a heuristic based, which means we do it by assuming, okay, this is about similar as it happened 1 minute ago. It's not always completely right, but usually it's quite okay. Because the thing is, if we don't do this, if we just say, okay, we process it at the end, we get very late results. But if we say, okay, we expect everything right away, always, or just with a minimal delay, then we don't have the correct data. And yeah, we can show this a little bit more, or I'll show this a little bit more later. But basically, this is what we thought of with Dataflow. Then we also thought, do we want to build a system for streaming data processing or batch data processing? Do we want to work? How do we want to work with these trade-offs? And why not make it possible to kind of work with complete data with latency, with streaming and batch model? Like, why don't we use something which can work with all kinds of data like this. And this is where the Dataflow, and I now call it also the Beam programming model, comes in. Now, why do we call it Beam? The Dataflow team, very soon they open sourced the whole programming model. And now they actually decided with teams from other companies which also work now with the Dataflow programming model to try to make it an Apache project. And just last week it has been granted, there was a proposal, just last week it has been granted incubator status, which means it's the first step to become a full Apache product like Apache Hadoop or something like that. And the name which was chosen is Apache Beam for batch and stream. So both should be possible with it, with the programming model. So it's nothing new, it's the same Dataflow was last week. It's now called Apache Beam as a programming model. The slide is very empty, there is not even a logo yet, for example, since it's just from last week. And it basically, it's the whole way of how to program this, the APIs, the SDKs, and some example implementation for a local runner. And there's different sponsors, Google for Dataflow itself, Cloudera because they implemented it in Spark, Data Artisans is the company behind Apache Flink, if anyone heard of Flink. And then there's a few other which are big users of Dataflow, which started sponsoring this proposal. So this is kind of towards an open future. We don't want this to only work on Google, we want this to work everywhere. And what is this Dataflow programming model? Well, we just want people ask themselves some questions. What data you work on, when in the time it comes in, when you process, so when did it happen, when do you process it, and what do you want to do if something is different? And I explain a little bit in the next slides. So what are you computing? This is the same as in Flume. You shouldn't have to think, okay, I want to map, I want to reduce. You should have some simple programming model. And you just have data coming in, and this data we call a peak collection, a pipeline collection. And then we have data running through the pipeline, and at the end data comes out. You shouldn't care what data. So this peak collection, it can be a bunch of data, a file, a bunch of files, or it can be streaming data through some queuing process. So you don't care what data you work with, it just runs through the same pipeline. And then we have the transformations, the P transforms, which just change how this data behaves. Either it's like a simple element transformation where you do something to every part of the data, or it's some aggregation model, you put some sums or something, or a transformation could be also made up of other transformations. And so it can be a more complex transformation, which you then can use one by one. Very simple example, and this is kind of the code. Basically, you can start with strings. You have some raw text in a text file or coming in streaming, where you have something which needs first to be parsed, like you have the gaming data comes in. I collected some coins, I did this, I did that. This comes in a raw format. Let's say the first thing you want to do a transformation, you want to bring it in a more structured format, where you say, for example, collecting coins, you want to change it into which user collected how many coins is the output. And for this, you just apply this function which you wrote, which is a simple function. Okay, take this separated by comma or something, and apply this to the data, and do this on all the data in parallel. This is this parallel do. So you don't care how it does it, you don't care how many machines it needs for it, just apply this to my data. And then the next thing you want to maybe say, okay, now I have a bunch of data which says this team or this user collected this many coins. Now you want to sum it up and want to see how many coins did every user collect. And this is actually the first example I will show it later. So you have again an output, and you just sum up for every user all the data points you have. So this you can do, and this is a very simple example. So this is also the example on how I show how you do this with different data types. So the traditional way to do this in batch, you have like, okay, let's say this is all the same user and he collects all these coins. And these events come in at a specific time and they get processed at a specific time. And I also put here the ideal time when the event would come in. Let's say some events are quite late, and some events, they come in quite quickly. This one comes in quite late. Like it only comes in at 12:08, but it happened at 12:01. So we have kind of both ways. In the traditional way, when you have one file and then you go through it, doesn't really matter. It counts up all the data it got, and at the end it gets the result. The user has 51 points. Now, this is less interesting. We talked about you want to have really some windows of time. You want to say, I want to see every minute what is collected, or every hour. Or you want to have sliding windows. You want to always know what has been collected by every user in the last 5 minutes. Or best, you want to have this by user sessions. And this is the kind of windowing. And in Dataflow, this has been built in. So basically, here you say, okay, I want to sum this up. But before I sum this up, I want to divide the data in fixed windows of 2 minutes. And that's what happened. It's kind of the same thing still. It sums it up now by every 2 minutes when the event happens, but you only get the result at the very end when all the data has been processed. And now you have it in 2-minute windows. Now this doesn't really help you much because you still wait till 12:10, then you have more granular results, but it's still the same result. Doesn't really stream because you don't have data in the middle. So this is where this watermark comes in, where you say, okay, we kind of know how fast this data is coming in. We try to figure out what we do when this watermark happens, like when I think it should come in. So we can put in this trigger. We want to say, at this watermark, I want to get the result. And this is how it looks then. Let's say this is the watermark. And this watermark is automatically calculated. You don't do anything for this. And it tries to give you results right away. And it gives you here a result already for the first window, here for the second, here for the third window, here for the fourth. But you can see there's one problem with this. This didn't make it because it came much later than expected. Like something happened there, the guy had a network delay which was too long or whatever. So it didn't even get calculated in. And this is always when you have just latency sensitive things, these things happen. You have like late data. Now, in real streaming data processing, you still kind of care about this. So you still want to work with this. And also you notice here the 3 happens quite early. And it still takes a while until actually the results get calculated. So you have the other result as well. So what we can say is we want to not only calculate it at the point where I expect all the data is there, but I want to give you an early estimate of every minute what might be the end result. And I want to give you late results as well whenever they happen. For example, this is another way how to calculate this. So every time something happens unexpected, I make a new calculation. So what then happens, let's start again, is that it goes through the data again. It comes to the same results. Here it gives you an early result earlier, and then the right result later. And here, once the 9 comes in, it immediately tells you, actually, I was wrong with this 5. In this minute, he collected 14 points. So this gives you the possibility to be more flexible. So yes, you can give the user a score every time, but you can have a correct score at the end, for example. Now you can make this even more complex, because what happens when this data comes in, and it depends. Here you say, for example, for this one window, you get the 3 early, you get the 5 and 1 at the right time, but you get the 2 late. So that gives a sum of 11 points. Now, how do you store this when you store the output? And there's different ways. You can either say you store whatever happens, which means you store 3, you store here 6, because the 5 and the 1, and you store here 2. Which means that whenever you look in the database, you need to look at everything which is there, and you need to add it together. Which means you need to make another calculation. Not so useful for some ways, maybe useful for other ways if you want to have more granularity. So you can say, okay, I want to calculate another way. So the first time I write the output 3, the second time I add the 6, I write the output 9, and the third time I write the output 11. So you always only need to look at the last point in the data set and see the real result. So this is good unless someone does what the first user does and just calculates all the scores together over the whole data set, then he gets a much too big number. But this is the accumulating way. And then to make it work for kind of in a data set where both of them kind of should work, you can accumulate and retract. So you can say, first I say the score is 3, and then I say the score is 9 and minus 3. And then I say the score is 11 and minus 9. So if you just calculate everything together, you still have the right score. But the guy who wants to only look at the last element, he just ignores the negative numbers and he has the right number right away as well. So this is the way of accumulating and retracting. And this you can put in the data programming model as well. So it gets quite complicated. So you can add this accumulating and retracting. So you want to say, I want to always have the right score and take off the other scores. And then we added another thing here to make it even more complicated. We say now we want to try to find out what is the user session. Whenever he didn't log in for 1 minute, it's a new session, and I want to calculate the new score for the new session. Instead of saying I want to calculate a new score every minute. And this gets quite complicated, but it's still just a few lines of code to provide this sum. And you see it now in the picture. Hold on. It gets quite complicated because over time, when this fires again, suddenly the session becomes longer and this becomes a huge session. So over time, the data changes shape and in both directions. But still, you can read from it at any time and get the best result you have at that point. So yeah, so it gets quite complicated, and Dataflow allows you to do all of this. You can just add up everything in batch. You can add up the whole thing with fixed windows. You can stream data in. And change the results if something comes in late or early. Or you can even do like a complicated function, just like I did with the sessionizing, where the session size changes as data comes in as well. So Dataflow allows you to do, or Beam allows you to do all of this. But I want to show you how this looks in Google Cloud Dataflow. And Google Cloud Dataflow is a fully managed service to run this. Now, I talked about how Dataflow works. Google Cloud Dataflow is just a product in our cloud where this is completely done for you. So basically what happens is it's done automatically. You just program the model and it brings, you give it the data and it brings up machines. It can scale the machines up and down if the streaming is coming in at different rates over the day, to be able to automatically process all data as it is coming in with a short delay. So this is one way how you can run Dataflow. You can also run it in other ways, because Dataflow or Beam is just an open source SDK. It's available in Java now. Python is in alpha status now and is in active testing. So once you program this, you can run it in different ways. You can run it on your own machine, obviously at a different speed. You can run it on the Dataflow service, as I will show you, or you can run it on Apache Spark and Flink, because Cloudera and Data Artisans, they developed the runner, so once you wrote a Dataflow pipeline, you can run it if you already have a cluster running Spark and Flink. Yeah, I said already, our service, we try to do some automatic optimizations on the code to make sure it can be efficiently executed. Scale up and down how many worker nodes you need, rebalance the tasks automatically, and then provide a UI and an API to monitor what's happening and if you got any errors, etc. So let me show you. Let me explain you what the demo is. It basically simulates a game. And in the game, just as I said, several users around the world, they collect points. The users, they all belong to some kind of teams. So depending on which team you are in, you collect points. So usually you want to know at every time what is the best team, what is the worst team, how many score did every user get, etc. And let's see. So this is my console. And here is basically just the code. I'm using obviously some fake data. Google doesn't write that many games. So I'm starting with some simple algorithm. Oh yes, let me try. How do I do this in Eclipse? Window.
Preferences. Type font.
Font.
In appearance.
Appearance Java. Java editor text font. Can I edit default? Yes. Let's try like this. Yes, okay. So basically this is the code. Before I show you a little bit of the code, I want to just run it because it takes a few minutes to run. This is the simple example, the first one I showed, which just runs over a batch of data. So if you want to run Dataflow, it has an Eclipse plugin, and you can also run it on Maven. Yeah, I have this user score. And basically you can say here where you want to run it. Do you want to run it on the local machine, or you want to run it on the Google Cloud Platform? And now I want to run it on the Google Cloud Platform. Let's hope it works. Yeah, and it's uploading the files. So basically you can try it out first on the same machine, on your own machine, and then it uploads. You can upload all the code to the Dataflow service, and it runs everything automatically. So this will take a little while to upload. While that happens, I can show you a bit how that pipeline looks, and we basically best start at the end. Yeah, at the main function. So basically here what we do is the same, kind of the same as you see in the pseudocode. We read some file, which I passed as a parameter. Then we in parallel run this parse event function, which basically the file comes in as a string, comma separated, and I made out of it the user, the time, the timestamp, and the score. After this has been passed into a function, I apply a new function which has been written, which takes the user and sums up the score for every user. And then the last bit is to write these to BigQuery. So you have several output options, several input options. Input options can be cloud storage, it can be BigQuery, and for streaming it can be PubSub. And same for the output options. So once you basically wrote this pipeline, and these are all just Java functions here, this extract and sum, and this parsing function, then you basically start running the pipeline. And in the programming model, you don't care where it runs, and you don't really care what kind of data it is. So this is how simple it is. Let me show you actually the parse function at the top. It's quite a bit more complicated than this most simple one could be. but basically it contains an element, and then it gets split by the comma. It creates a game action info object, which has the user, the team, and the score, and the timestamp. And then it outputs that. And if there's a parse error, it adds this as an error message on the console. So let's see if this already is running. Oh, actually, this I can show you. This is some example of the input data. So there's, as you can see, it's same. It's kind of fake data. It's just has weird usernames and weird team names, and then there's the score, and then there's the timestamp. So this is being processed. It's not really big data. It's 2 input files with 12 GB each. So yeah, it can run on just a couple of servers. But let's see if the pipeline started. So basically, this is the Google Cloud Platform console where you use all our Google Cloud Platform products. I want to now use Dataflow. And I see all the jobs I have running. The last one is the user score. It is running right now since 2 minutes 56. And here, basically, then you see in the UI, you see it the same way you've written the code. Like, you don't need to think about what it actually does. You see what you've written the code. You see the text I read. Then you see how it's parsing 1 million elements per second. And then you see this extract user score right now is running. But you can dig in. So if a function is if one of these transformations is a combined transformation, you can dig in and see basically the elements of it. So this extract user score uses two functions which are part of Google Dataflow, map elements and sum per key. And the map elements is already running, and the sum per key basically is then happening out of this output. So at the end, it will write the user data to BigQuery. So what you can see now, for example, you can dig in from the input file. It read already 135 million elements, 9.56 gigabyte of data. I told you it's 2 times 12 gigs of data. So it's approximately halfway through the data which I gave it. I didn't assign too many machines to it, actually. On the batch, you need to select how many machines, because either you want to have this run very fast with many machines, or maybe you want to run it slower with fewer machines. You can see also if there's any errors, any warnings. You can see.
Control plus helps.
Oh yes, that will help a lot. Sorry. Is this better? Yes. So here you can see kind of the job name, the ID, but also you can see anything which has been output during the pipeline. For example, there have been some parse errors. So the fake data contains some errors as well, just to make it more realistic. And so you see that happening through the pipeline as well. You can see in the logs what's happening. It started up 3 machines for this and started running this pipeline. Basically, just summing up. Well, it needs to combine. It needs to basically, because it's batch, it needs to wait until all the other stuff has finished. So this will take a little while. So while this is running, I show you a bit more complex pipeline where we use the streaming process. And because it's streaming data, I ran it for about a day. And let me show you. The first one is the one basically creating the leaderboard. And the leaderboard, that one is running already for a few days. And it basically has elements coming in all the time, about 1800 per second, which get moved through the pipeline right now. I don't know if it changes a little bit in speed over time. What happens? So here you can see a streaming pipeline happen. And the interesting thing is here you can always also see this lag and the watermarks, basically when you expect the data to come in. It's a bit more complex pipeline. Basically, it also parses the event and it creates 2 leaderboards, one by team and one by user, just to make it a bit more complicated. And when you can see now, for example, maybe here at the end. Here you can see basically when it creates these fixed windows for the leaderboard, it's 5-second lag from the data coming in till it gets processed. So it tells you it has now processed the data, it thinks, up to 1954-02. Well, don't know. Yes. So, however, if something comes in late, it will use this kind of function. And I can quickly show you the code there as well. This is the leaderboard. It's a bit more complex, but basically it does the same thing. We've seen earlier it creates 2 different pipelines or 2 different transformations on the past data. One for the user, one for the team. This is the user one. And the user one, we say it should trigger repeatedly. It should accumulate the data, late data as well. And then it should sum the scores every minute, basically, and write them to BigQuery. And for the teams, where is the teams? It's on top of that. It uses fixed windows of 1 hour, and it will, every 5 minutes, it will try to get you an estimate already, what is the result. And every 10 minutes after the time is over, it will give you late data. And at the end, again, in this case, it will write it to BigQuery. So this is how you can see it on how it's being written. Obviously, once it's like there's 1800 elements coming in, but there's 0 per second being written, because obviously when it writes these sums, it writes them every 10 minutes. This is still 0 per second. So it's quite harder. Now let's go back to the first pipeline. It has finished. And you can see everything has succeeded. And why did it not? Yeah, exactly. It tells me it has written out 292 kilobyte out of these 2 BigQuery. It's not really big data anymore, out of the 25 gigabyte. So basically with Google BigQuery, I will also make this bigger. It's our SQL data analysis product. Let me reload this. So it's written it in this data set. The first thing is the user score, which is just the batch result, how it written it up. Now I can query the table and see the total score for every user. I think it's this one. And I get the result. And you can see even in the fake data, we put some fake spammers in. So the first results are all the robots. And then come the real users with their score. So basically, if you look over, this is over the batch, over the batch data, over just a few files. If you use the same over the streaming data, let's say we get the leaderboard. It looks pretty much the same. And this changes all the time. The high score now by user is still the robots are all on top. And then comes the real users. So this is why we have written a even more complex example, even more complex pipeline. And all these examples there on GitHub, so you can try them out yourself. Let me show you. The game starts pipeline takes the same data, reads it, parses it, extracts it, but then it does different things from it. It also tries to do some spammer detection by seeing if something has too many points, for example, to see where too many events come in from one user too fast, and filter these spammers out of the results, and then write the sums. So if you run the same kind of query over this example, where is it, anti-spam? Then you get, for example, the real users by their total score. Here I even have written the windowing times. So, for example, every hour it can collect the score and can give you a new high score list.
So, to understand correctly, it filters out all robots.
It filters out all the robots. Well, it's again fake data, so everything is a robot, but it shows you how you could do some robot detection on your own data in this example by using some other heuristics to try to find something which doesn't happen in real data. So basically you can build pipelines any complexity, and you can also use them in parallel. So for example, if you can filter out the robots later, you can first have them in, or you can filter them in but still keep them in another data set just to make sure if someone complains later, hey, you filtered me, I'm not on the leaderboard, but I have a really high score, you can manually check. So you have any kind of complexity and run all this on the data in parallel. Like I use now BigQuery, you can also write this data and pops up again and publish it on a web page in real time, for example. All right, so that was the demo, basically showing you have different kinds of transformation. You can use the same transformation, the same code for batch or streaming. All of these examples, they use the time when the event happened and not when it came in. And then you can use it to kind of adjust the windows as you want. You can use the same data and use different sessioning or windowing method depending on what you need. And basically that's the end of the presentation. So I have a bit of time for questions, I think.